Hello and welcome to the final lesson of chapter number 1, and in this lesson we're going to look at homogeneous linear systems. A homogeneous linear system is just a special kind of linear system that we've already been looking at in the previous lessons. Specifically, a homogeneous linear system is when b is equal to 0. And by b is equal to 0, I mean that all of the numbers on the right-hand side of the equal sign are 0. So what I have here at the bottom of the slide is I have two different linear systems. One is non-homogeneous and one is homogeneous. If you want to determine whether or not it's homogeneous, you just look at the values on the right-hand side of the equal sign. This first system is not homogeneous because not all of these numbers are equal to 0. But the second one over here is homogeneous because all of the values on the right-hand side of the equal sign are 0. Now you might wonder what the importance of homogeneous linear systems are, and that's a really good question. In my opinion, there's no sense in labeling something unless it has an interesting property or properties that you're going to be talking about. And there's a theorem here that sums up the main idea of homogeneous linear systems, and that is that these special linear systems are consistent. So a homogeneous linear system will never be inconsistent. It's always going to have a solution. So it will always either have a unique solution or infinite solutions. This idea of a homogeneous linear system always having a solution leads to two new definitions. And the first one's called the trivial solution. We say that a homogeneous system has the trivial solution if every single value that we get for all of the variables is 0. In other words, the trivial solution is the only unique solution that we can get when solving a homogeneous linear system. And the second type of solution we might get is called non-trivial solution. The easiest way to think about non-trivial solution is that it's going to be an infinite solution. So to sum both of these definitions up, if we solve a homogeneous system and we get a unique solution, we call it a trivial solution. And if we solve a homogeneous system and we get an infinite solution, we call it a non-trivial solution. So let's go ahead and solve a couple homogeneous systems so you can see how they're solved and how we label them. Just like before, the first thing we're going to do is we're going to transfer our linear system into its augmented matrix. And then once we have our augmented matrix, we're going to start working on getting our leading one and then canceling out any entries below that leading one. So our first leading one would go here. But notice that if we divide row 1 by 2, we're going to end up with fractions. So I'm going to save the division by 2 until the very end. I'm going to use this 2 to get rid of the number 4. I'm going to do the operation row 2 minus 2 row 1s. Now next I'm going to look to put a leading one in this position, but again if I divide row 2 by 5, I'm going to end up with a fraction over here. So instead of obtaining fractions, I'm actually going to switch row 3 up into row 2. Next, let's create a leading one by dividing row 2 by 2. If we perform the operation row 1 plus 3 row 2s, we'll create a 0 above our new leading one. And to create the 0 below our leading one, we'll do row 3 minus 5 row 2s. Now that column 2 is complete, we can go ahead and create our next leading one in column 3, and we can do that by taking row 3 divided by 9, or 1/9 row 3. The operation row 2 plus 2 row 3s will create a 0 above that leading one. And then the operation row 1 plus 5 row 3s will give us the second 0 above that leading one that we need. And the last operation that we have to do here to get to reduced or echelon form is to take row 1 and divide by 2. So here is our reduced or echelon form augmented matrix. And what we can do is we can read off row by row. So row 1 tells us that x must equal to 0. Row 2 tells us that y must equal to 0. And the third row tells us that z must equal to 0. So here's the solution set of our original linear system. Since we began with a homogeneous system and we ended up with a unique solution, we call this solution the trivial solution. So let's work through one more example of homogeneous linear systems. Take the time now to pause this video and transfer this into an augmented matrix and try to do elementary row operations until you get to reduced row echelon form. So here's our augmented matrix, and I'd like to have a leading one up here, but notice that if I were to divide by 2, all of the entries over here would become fractions, and that's going to get really messy. So I'm going to do a little sneaky trick here. I'm going to take row 2 minus row 1. And I'm going to essentially use this 2 like a leading one to create a 0 down here. And that worked out a lot nicer than I thought it was going to. We end up getting zeros in these 3 entries, so now all we have to do to get row 2 in good shape is to divide by 2 to create a leading one here. So that's going to be my next step. I will divide row 2 by 2. So let's go ahead and use that new leading one to make a 0 above it, and we can accomplish this by doing row 1 plus 3 row 2's. And our last step here is just to go back here and create a leading one in this upper left-hand spot, and we can do that by dividing row 1 by 2. Now I think what's important to note here is that I've created this leading one last, and the reason I skipped out on dividing by 2 in that first step is to prevent the fractions that are going to occur here in row number 1. So just a little tip as you're working through your linear systems, if you have to, do these divisions last, and that way you're not going to be bogged down by crazy fractions in the middle of your operations. Try to create those fractions as far down the line as you possibly can. So take the time now to try to set up this infinite solution. Note that we do have an infinite solution because we have 2 leading ones, yet we have 2 columns that do not contain a leading one. So we are going to have 2 parameters. Try to find that infinite solution now. We're going to start by setting up our parameters. Since there's no leading one in column 3 or column 4, we set x3 and x4 equal to s and t. These are our 2 parameters, and s and t are allowed to be any real value. So here's our corresponding linear system that we get when we sub in x3 equals to s and x4 equals to t. And what we have to do is just solve that first equation for x1, and we'll get that x1 is negative half s plus half t. And from here we can write down our solution set. So we just solve for x1, so we'll just copy that back down. Up here we have that x2 is equal to 0. x3 is one of our parameters, it's equal to s, and x4 is also a parameter equal to t. Since we started with a homogeneous linear system and we ended up with an infinite solution, we call this a non-trivial solution. So a couple ideas to leave with you at the end of this video. And the first one is that any linear system that has more variables than equations is called underdetermined. And these special kinds of linear systems, it's impossible for them to have a unique solution. Okay, the reason why they can't have a unique solution is because they end up having more columns than the number of leading ones that we can get in there. And this leads us to a really important idea about homogeneous linear systems, and that is if we have a homogeneous linear system with more variables than equations, then it has to have a non-trivial solution. That's exactly what we saw in example number 2. Okay, so example number 2 is a homogeneous linear system that has more variables than equations, and we did end up getting a non-trivial solution. Okay, and as we come to a close on our chapter on linear systems, there's kind of this overarching question that we probably should ask, and that is about the applications of linear systems. And of course, there are quite a few applications of linear systems. I know that the textbook has a couple. You can use linear systems to solve electrical circuits, to solve chemical balancing equations, to solve traffic flow. It might be possible to take a look at some of those applications if we have some time, but otherwise I do encourage you to go take a look at some of the applications inside of your textbook. Alright, my little epsilons, stay positive.